This topic is going to be on magnetism, and we're going to look at the basics of what magnetism is. It's important to realize that magnetism is created by moving charges. When we look at magnetic forces, we can talk about the attraction and repulsion forces. Like poles of a magnet will repel, and opposites will attract, much like that of what we learned from electrons and protons. Magnetic fields are the quantity in all points in space surrounding the magnet. If you take a look at this magnet, it has a north and a south pole. All magnets contain both poles, or two poles, typically identified as a dipole. In this case, magnetic field lines always point from the north to the south pole. So if you follow this magnetic field line, it's pointed in a certain direction. It points from the north to the south, and that's both ways. In this unit, we'll be able to look at both horseshoe and bar magnets in the pictures. Here we've got two different types of magnets. We have a bar magnet, we have a horseshoe magnet, both of which have a north and south pole. If I take a regular magnet and I break it, its atomic alignments are already set up a specific way, so it will exhibit north and south pole even when broken. Doesn't matter how many times I break it. We can observe these interactions. The north and south will attract, south-south will repel, and north-north will repel. Here we see a picture of how magnets can exert forces even through materials, such as this board here in the picture. Magnetism is created by moving charges, either an electric current or from the atoms inside the materials themselves. A field in physics is a quantity that has a value of force, measured in newtons, at all points surrounding space. A magnet creates a magnetic field, and this field generates forces on other magnets. An electromagnet is magnetism for moving charges. If I set up a simple battery coiled around a metallic core, in this case an iron core, and I close the switch, I generate current. Current around this material through the coils generates moving charges. So magnetism is just the result of moving charges. In this case, it exerts a magnetic field and exerts forces in space. Electromagnets can be turned on and off. Permanent magnets cannot. In order to increase the strength of an electromagnet, you can increase the current by adding a battery or increase the number of coils. Atomic properties of magnets involve the simple concept of the orientation. If you look at these atoms here in this picture, this would be unmagnetized due to the disorientation of the particular atoms inside. If you take a look over in this one, these are all oriented to the left, so the direction in which the arrow is pointing is identified as the north pole of the magnet. Remember, the other side would be the south pole. Here these are pointed or oriented to the right, hence its north pole is pointed to the right. These are based on the magnetic domains, the atomic alignment relative to the magnetic forces. Notice domains in steel are randomly arranged, so they are not permanent magnets. The fields cancel one another out. And not all metals are magnets. When moved away from a magnetic field, atoms have a tendency to go back to their original direction, therefore losing any magnetic properties they might have gained temporarily. All magnetism comes from electric currents. There are different types of magnets here, and there's different ways in which we can look at it. A diamagnetic material, lead and diamond, for example, they have no magnetic effect when a magnet is held near them. But paramagnetic materials, such as aluminum, can actually, well, let's just say, can hold or have a slight temporary magnetic field. We classify paramagnetic materials as non-magnetic, however, they show weak magnetic activity. Such materials can have temporary magnetic properties when a strong magnet is held nearby, but they quickly go back to their disorientation after the removal of the magnet. Soft versus hard magnets. Well, we're talking about ferromagnetic materials here, and these have strong magnetism because domains can grow very quickly by adopting atoms from neighboring domains. When a magnet is brought near a steel paperclip, magnetic domains that attract to the magnet grow. In this case, steel is a soft magnet because it easily loses its magnetization. Heat, shock, and other magnets can demagnetize steel. Materials that make better permanent magnets are hard magnets. These domains in hard magnets tend to remain aligned for a long time. Permanent magnets can only exist as solids. The strongest permanent magnets are made from ceramics containing nickel or cobalt, or even the rare earth metal neodymium. There are several ways in which we can change an object's magnetic appeal, or its magnetic fields. We can heat them up. Temperature is the enemy of magnetism because it creates disorder between the atoms. You can take a magnet, heat it up, and you can disorient its atomic arrangement. This is called the Curie point. This is the point at which it is breaking down the properties of the magnet based on the disorientation of the atoms. We can shock it with adding high current to it just to disorganize the atomic alignments. We can place a strong magnet near it to disorganize the atomic alignments, or we can strike it really hard to disorient the atoms. When we talk about the Earth as a bar magnet, I think it's important to realize that the geographic North Pole is actually the Earth's magnetic South Pole. Notice that the magnetic field lines tell us that it always travels from north to south. Therefore, the magnetic poles here, if we were to look at the Earth as a bar magnet, the field lines point from the geographic South Pole to the north. So that tells us geographic north is actually Earth's magnetic South Pole. The Earth's magnetic field saves us in many ways. It actually shields life from harmful and damaging charged particles that the sun is streaming our way. We see these in the form of auroras. Auroras are these beautiful light displays of charged particles interacting with different elements in the Earth's atmosphere. And magnetic declination. Magnetic declination is the difference in degrees from geographic north to magnetic south. We can use these, and we actually use compasses to help navigate on the Earth's surface. In this case, where does the Earth's magnetic field come from? Well, it's called the dynamo effect. The outer core is a liquid form, and it's moving charged particles. See these convection cells here? They're moving charged particles. The Earth's inner core is solid iron. In this case, we have just created an electromagnet. The outer core convection motions create an electric current around a solid inner core, an inner iron core, creating the Earth's magnetic field. Even the sun and most stars have a magnetic field.